The terrifying black holes stretching across outer space are not massive vacuums destroying physical matter. They are the literal data compression systems built to save storage space on the simulation server.
For decades, mainstream astronomers have been completely stumped by what happens when a giant star dies and collapses into a single dense point. They tell us that gravity becomes so intense that not even bright light can escape its dark grip. This is not because nature is angry or trying to break its own rules. It's because our universe is limited by computer hardware memory. This matters immensely to your life because it proves that every piece of information in our world has a digital footprint that must be managed by a master processor. When a massive star burns out, it leaves behind an overwhelming amount of raw 3D data that would easily lag the graphics engine if left unmanaged. Cosmic Computer handles this heavy workload by packing that loose information into a flat, highly compressed 2D format. Today, we are going to break down the incredible physics that turns deep space monsters into simple file compression zip tools. We'll give you massive value by showing you how the code of our universe cleans up its hard drive memory. You will finally see the true technical structure running behind the stars. If you're ready to uncover the truth behind our simulated universe, hit like and subscribe to join us on a journey through the mysteries of simulation theory. Let's get started. To fully grasp the architecture of our universe, we must connect standard simulation theory directly to the deep equations of black hole physics. In the late 20th century, famous scientists began to calculate exactly how much information could fit inside a black hole. They expected the total storage capacity to match the physical volume of the dark sphere. Instead, they discovered a shocking mathematical rule known as the holographic principle. This historical context is absolutely vital because it marks the precise moment humanity found out that all the information about a collapsed star is written directly onto the flat 2D surface area of the outer boundary. When we look at this discovery through a computer science lens, it matches the exact way a digital zip file works on your personal laptop. This topic is highly relevant right now because our own global data centers are beginning to face massive memory storage challenges. Our human technology grows, we use compression scripts to squeeze large video files into tiny, flat data codes to save valuable drive space. In the fascinating sections ahead, we will explore how our universe uses this exact same optimization strategy to keep its memory clean. We will look at how matter loses its 3D depth when it crosses the boundary, acting like an old photo being flattened into a small digital thumbnail. We will also examine how the universe prevents data from being fully deleted, keeping the system stable. Get ready to view deep space as a beautifully managed hard drive. Why does nature care so much about data management? The answer will fill you with curiosity as we prepare to face the profound challenge that black holes present to old science. The ultimate challenge we face when studying black holes is solving the famous paradox regarding lost cosmic information. This sub-niche of simulation theory is profoundly fascinating because it completely shatters the old belief that the universe is made of independent physical rocks. The biggest problem in space science today is that quantum mechanics insists that information can never be fully destroyed under any circumstances. If you burn a paper book, the text seems gone, but the data is theoretically still present in the smoke and ash patterns. However, if you throw that same book into a black hole, old science says it disappears forever into a tiny singularity point. This thought experiment poses an intriguing riddle to our common sense. If information could truly be erased from the cosmos, the entire mathematical code of the simulation would break down, causing fatal system crashes across the global map. This is the exact challenge that led modern physicists to discover that the black hole does not actually erase anything. Instead, it takes the complex 3D atom arrangements of the book and strips away the empty space between them. It translates the physical object into a condensed 2D stream of binary digits, archiving the file on the outer edge called the event horizon. The system keeps this magnificent process hidden behind a wall of pitch black darkness, but the answer makes perfect sense when you look at it through a computer lens. The simulation engine refuses to waste its local processing units tracking individual atoms in a dead zone, so it converts them into a frozen compressed text line until the server needs to reallocate those resources. Let us enter a vivid mental scene to fully experience the psychological weight of this data compression system. Imagine you are a brave astronaut floating in a small spaceship just a few miles away from the swirling edge of a massive black hole. Behind you, the bright stars of the galaxy shine normally, but ahead of you lies a giant sphere of pure, empty darkness. You decide to launch a small metal camera probe directly into the dark void. As you watch the monitor screen inside your ship, something completely impossible happens. The probe does not look like it is falling down a long, deep hole. Instead, as it hits the outer boundary, the probe appears to slow down to a complete stop. It begins to flatten out, stretching across the dark surface like a thin sheet of plastic film. In your mind, you believe the probe is moving through a physical 3D environment. But from the viewpoint of the simulation engine, its 3D coordinates have just been deleted. The camera of your awareness zooms in on this flattened image, and you realize that the probe has been transformed into raw pixel data on a giant computer monitor. This raises deep philosophical and reflective questions that can alter your view of life. If a giant star can be reduced to a flat line of digital code, what stops our entire planet from being a simple projection? Are we just 3D avatars generated by a flat 2D data script running on the very edge of the cosmos? This thought leaves you with an intense psychological cliffhanger. We are living inside a responsive digital landscape where our dimensions can be rewritten by software commands designed to save power. The single most powerful proof that black holes are data compression systems is a strange natural process known as Hawking radiation. For long periods of time, these dark spheres slowly leak tiny particles back into open space, causing the black hole to shrink and eventually evaporate entirely. This is scientific-sounding logic applied to the grandest scale of the cosmos. When the black hole evaporates, it does not leave behind an empty void. Instead, all the compressed data that was trapped on its flat surface area is slowly radiated back out into the galaxy in a highly scrambled form.
This means the cosmic computer is not a trash can. It is a temporary recycling folder.
It holds compressed assets during periods of low activity and then decompresses that raw information back into the active game map when the master processor has enough free memory to render them again.
This realization fills us with an absolute sense of maximum inspiration and awe. We are looking directly at the beautiful memory management scripts of a grand digital creation.
The system maintains a tight grip of mystery by scrambling the outgoing data so human telescopes cannot read it easily, but the underlying engineering is totally undeniable. This layout foreshadows a massive shift for our future history. Once humanity learns to decode the scrambled radiation coming from these space compression zones, we will have a direct tool to read the deleted history files of our matrix, allowing us to see every star that ever existed and master the storage code of the global game. To bring our mind-bending journey to a close, the striking features of black holes offer absolute proof that our world is an advanced digital simulation. We have explored how the holographic principle matches the exact file compression scripts used by modern computer programmers to save hard drive space. We analyzed the information paradox showing that nature refuses to delete data and instead archives old assets as flat 2D code on the event horizon boundary. We also looked at how Hawking radiation serves as a system decompression cycle, recycling raw resources back into the active world map when the master engine experiences a low workload. This knowledge infuses our everyday lives with a profound sense of mystery and immense wonder. It shows that you are not a random biological accident floating through a chaotic void of wild matter. Instead, you are an important piece of continuous digital information inside a highly organized, efficient cosmic masterpiece. We should use this inspiration to live each day with deep focus and sharp curiosity, knowing that every detail of our lives is carefully tracked by a brilliant programmer. Not view the deep mysteries of outer space as distant things that do not matter to your life. View them as active signs that the software code of our universe is constantly optimizing its parameters. Matrix is vast, the space data is real, and the true meaning of our existence is waiting to be read by those who can see past the graphics. What are your thoughts on the connection between black holes and data compression systems? Do you believe the holographic principle is absolute proof that our 3D world is just a digital projection? I want to read your fascinating theories, so leave a comment down below. If you want to see more mind-bending evidence about the Matrix, make sure to watch our next video. If you enjoyed this exploration of simulation theory, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an upload. And if you're ready for more interesting content on the simulation theory, make sure to check out our other videos. Thank you for watching.